Państwa bardzo serdecznie w stacji paryskiej Polskiej Akademii Nauk. Vous êtes ici dans un endroit qui me semble très intéressant, pour ne pas dire extraordinaire. Jesteście Państwo tutaj w miejscu, które wydaje mi się nie tylko bardzo interesujące, ale w ogóle wyjątkowe. Au début du XXe siècle, Marcel Proust, par exemple, fréquentait ce lieu. Puis après, il y a 100 ans, il y avait des grands Polonais, des grands noms des Polonais qui étaient là, ici où vous êtes aujourd'hui. C'était entre autres Marie Curie ou un certain Paderewski. W tym miejscu na początku XX wieku przebywał Marcel Proust albo wiele osób innych, pośród których starczy wymienić 100 lat temu była tutaj Maria Curie-Skłodowska czy Paderewski. Je voulais remercier deux personnes, on va remercier les autres, mais notamment deux personnes qui ont justement contribué à ce grand événement qui est votre colloque, à savoir messieurs le professeur qui sont là, merci beaucoup, et encore madame la docteur qui est à côté de moi. Chciałbym podziękować tutaj w tym miejscu w pierwszej kolejności obu panom profesorom, którzy tutaj zasiadają, i pani doktor, która stoi obok mnie. C'est l'année de collaboration extraordinaire entre la Pologne et la France, l'année exceptionnelle. Donc je veux aussi remercier tous ceux qui sont là pour justement renforcer cette collaboration scientifique entre les Polonais et les Français. Jest to rok wyjątkowy, rok nauki polskiej. Chciałem Państwu wszystkim podziękować za to, że wzmacniacie swoją obecnością, swoimi dysputami, swoimi referatami, dalszymi projektami właśnie ten. Et je cède la parole à madame la docteur. I oddaję głos pani doktor.
Dear co-organizers, dear guests, my name is Magdalena Sajdak and it is my privilege and pleasure to welcome you here today. We are delighted to have you with us during this conference on modeling methods and computer systems, networks and bioinformatics. We know that many of you have traveled long distance to be with us. Thank you for coming. This year we are celebrating the French-Polish Scientific Year. Today's conference is a perfect example of cooperation between the two countries and our research institutions. We hope that events like this one will strengthen the cooperation even further, and we will have more successful events like this one in the future. And before I hand over the voice to Professor Gelembe, I once again like to say thank you to all the co-organizers, the co-sponsors, and everyone who has made this conference possible. Thank you very much.
Je vais m'exprimer alternativement en français et en anglais, en imitant un petit peu la technique utilisée par le directeur, monsieur le directeur, historien connu, qui nous a fait la traduction. Alors, pour ce colloque en particulier, ça a été organisé de façon un peu inattendue. Je faisais un déplacement en Pologne, effectivement à Varsovie, et j'avais eu l'occasion de rencontrer à Varsovie le conseiller culturel français qui m'avait parlé de la collaboration franco-polonaise et de sa célébration du 100e anniversaire. Je me suis dit, tiens, on est en plein dans la chose, mais je crois qu'on m'entend. On est en plein dans la chose, et en fait, on a une collaboration depuis 40 ans, depuis le début des années 80. Donc c'est dans ce sens-là que je suis venu ici. J'ai rencontré monsieur le directeur, j'ai rencontré Magda, on a eu des discussions. Le même jour, on s'est rencontrés tous les trois, et cette initiative a vu le jour. I switched to English, sorry for those of you who don't understand French. There aren't many, but there are quite a few anyway. So this whole event was initiated, in fact, on a trip that I took to Warsaw and had a chance to meet the French cultural counselor there, Christophe Paoli, who is an engineer actually. And he mentioned on that occasion that there was a year being celebrated this year, 2019, for the 100th anniversary of French-Polish scientific and cultural agreements or collaborations. Of course, historically, if you think of Marie Curie, it goes even further, much further than that. But this was a formal, because for a long time Poland as a state did not exist, so you had to wait for the Sèvres Treaty for Poland to exist as a state, able to sign. Before that, it was Russia, don't forget. For Poland to sign agreements, collaboration agreements with foreign powers, other powers. So I think it was in 1919 that the agreement was signed after the Sèvres Treaty, and it has been going on since that time. And this year we are part of the celebrations. We obtained the patronage, in particular, of the joint ministries of foreign affairs of Poland and of France for this event. Okay? The event itself is based on contacts with colleagues. It represents the work, the fields that we have developed over the years, but it opens to areas which are adjoining, scientific areas which are adjoining our main field, which is the mathematical modeling of computer systems and networks. That's the main field. But then we open this towards bioinformatics. One reason that I have worked on bioinformatic models, one reason, but also because my colleagues at the University of Nice, with whom I collaborate, are very active in the field of bioinformatics. And this represents actually a very good extension or collaboration between adjoining fields that use similar methods, comparable methods. So that is the scope. And we are very fortunate to have, in addition to Polish, very distinguished Polish speakers, very distinguished French speakers, we have the good fortune to have some friends from America here. And you may have noticed that there are 2 papers from the US, there's 1 paper from Greece, 2 papers from Italy that are being presented. In the case of the American colleagues, one of them is a false American or a true Pole. I don't know which one I should say. Professor Szymanski is in fact in the US, but he's also a fellow of the Polish Academy of Sciences. So I thank all these colleagues who are here. I thank my fellow organizers, Tadek Czakorski, Krzysztof Groszla, who did a lot of work for the organization, who's sitting in the back. I thank them for being here and also for doing a lot of work. And I'm really grateful to my colleagues for participating and to the students, both Polish and French, who are here. The Polish students had to travel quite a while, quite a distance. The French students had to come all the way from Versailles and Saint-Quentin and whatnot, but I'm very grateful to them. And I'm grateful to colleagues who induced, such as Jean-Michel Fourneau, who induced the arrival of these students to the meeting, because we have to prepare the future. I mean, we can't just do research and tell ourselves what we did before. Now we have to go forward and have young people get involved. Avec cela, je termine. Je remercie donc Tadek Czakorski, je remercie Christophe Groszla dans l'organisation, je remercie Magda, qui a fait, docteur Sadiak, qui a fait un énorme travail d'organisation aussi. Je remercie aussi monsieur le directeur qui a été vraiment un très fort soutien, très enthousiaste dès notre rencontre. Et merci à tous d'être ici, aux étudiants de Versailles et de Pologne surtout, qui ont fait ce voyage long pour nous rejoindre. Alors, à partir de là, je crois qu'on va commencer les présentations. Quelques informations pratiques, rapidement. Les toilettes sont au sous-sol. Ça, c'est toujours utile à savoir. -1, j'ai vérifié. Vous descendez, si vous sortez de l'ascenseur, elles seront en face de vous. Ensuite, on va essayer de garder les présentations à 25 minutes. Et certains autres seront plus courts, mais en tout cas, on va essayer de faire des présentations de façon à tenir un programme qui est relativement dense. Il arrive toujours qu'on ait 1 ou 2 absents parmi les conférenciers, ça donne un petit coup d'air à respirer, mais ça ne résout pas totalement le problème. Donc, nous avons en début de matinée, donc dans la matinée, c'est 4 conférences, ensuite des conférences qui se succèdent toute la journée. Et puis, comme vous le savez, il y aura donc un déjeuner qui sera servi dans la salle au fond. Et après les présentations, en fin d'après-midi, vers 18h, 17h30, 18h, on prendra un verre aussi dans la salle de fond. D'accord? I switch to English. So, for those of you who haven't discovered it yet, bathrooms are in the floor -1. So you take the lift, if you go down 2 floors, then you will see the bathrooms just across. I went down to check. It's there. And with respect to the organization, we will try to have 25-minute presentations because our time is fairly tight. You see, we have quite a program. Lunch will be served in the room in the back. And at the end of the day, around 6 o'clock, there will be a drinks reception in the same place. Okay? I think I finished all the organizational matters. And I pass the microphone to Tadek, who is going to talk a little bit about, Professor Jankowski, about the history of this collaboration, which started 40 years ago, practically, in around 1980.
So, I noted here just a few facts and 2 names. It is my personal view on our relationships with French colleagues, French friends, and it is from perspective from one small laboratory in our country, which is not in Warsaw, it's the smallest institute in the Polish Academy of Sciences and Technical Sciences. I say it to say I don't know the numbers, but if you multiply it by the number of institutes of Polish Academy of Sciences, by number of universities, it should be quite impressive statistics. So, it's even earlier. Sorry. Okay. Thank you. So it's even earlier than Errol told. I'm here coming back to the foundation of our institute. It was in 1968, and our teacher, our master, Automata, Stefan Mencken, who contributed a lot to Polish science, was graduated in Toulouse. It was in 1960, and the subject of the thesis was the analysis of trending states in systems with distributed parameters. And he published a number of books in France. Here there is an example. Les bases de l'automatique industrielle, Cheminement, 1965. When he established our laboratory, 2 eminent people were coming and bringing us the feeling of international cooperation. One was Jean-Charles Gilles Mazani. He était collaborateur Mark Pellegrin, and he was un centre de recherche automatique CELA, PNS de Paris. It was somebody of Renaissance character. He was at the same time a physician, a psychologist. I cite here his work on our poet Adam Mickiewicz, poète national de Pologne, et puis de psychoanalytique, caractérologique chez Dollarmer, he's and the other person who came frequently was Professor Pierre Vidal from Toulouse. Then he worked Université des Sciences et Technologies de Lille. And then we had a long collaboration with this institute. They wrote, for example, two books cited here, Development Systems and the Crossroads of System Theory, and the other introduction. Introduction à la critique de la stabilité dans l'espace métrique. Donc, ce sont our rules. And here I come to the fact mentioned by Error, Stefan mentioned Error met in Ilya Rocampour, and Stefan was interested by pioneer work on Neuronal, on the analysis of computer networks and the utilization of viewing theory in this analysis, and then introduced this domain in our institute, and I was charged to develop it. So I started also to visit France. I spent one academic year in Jerusalem with Raymond Marie. It was a marvelous time for me. I felt a member of his family, and I had a lot of time to prepare my habilitation this time. I met also the Rabbi in office here. Now he knows the Quran and others. And then I started to be an Error's Laboratoire d'Informatique de Systèmes Expérimentaux et de Modélisation, which was inside the building of LLI, Laboratoire de Recherche Informatique. Of course, I met beautiful, marvelous people. It was very international laboratory. I would like to cite here René Jamier, who was in charge of many things in the laboratory. And then we started, our group, our institute started to cooperate with former PhD students of Error. I cite here the most distinguished, Jean-Michel Coulon, the priest, other side, Ferrand Peckerly, Eddie Pellet, Turina Panjan. At this time it was INN, Institut National de Télécommunications, avec Michal Peckerlin, Université Créteil de Mar, et Louis Samicou, who is now in Maroc, but at the end we cooperated also. And we made together 10 projects, PANS and RS. So French, Polish projects, also 2 projects Pologne, so supervised by Foreign Affairs Ministry, and also some other international projects between Slovak, Romanian universities. And I just cite a few titles of these projects. There were much more. New methods of modeling and performance evaluation of high-speed networks, simulation evaluation of routing algorithms or optical networks. So it was all about modeling and performance evaluation of computer networks. And yesterday evening I counted publications we had. It was 96 conference and journal. It is about our institute, but I should mention here some other poles which were involved during this history in our collaboration. Many, most of them, Wojciech Selar. I met him in Israel when he was reading a book with Error. This book was concurrency control in distributed database systems. Now Wojciech is in Poznań. He contributed to Franco-Polish School of Bioinformatics and Communication communication technologies in Poznan, and then now he is a professor at the University of Poland. And he phoned me yesterday evening asking to pass his greetings. He's thinking about our meeting today. In Poznan, in the school, occasionally I was teaching just an anecdote, the use of QNAP. QNAP was very useful French program, Dominique Potier. I used it 20 years or more, and my colleagues also. It was, well, our models are computational models, so to have results, we need to have a software tool, and QNAP was excellent. So this is a past, a long history of work and friendship, I should say. But we are still going on. Some just mentioned two our Polish colleagues, which are now working in France. Andrzej Duda, former PhD student of ERO, who is now in Neuronal University, and a head of a group dealing with network protocols and multimedia application. And Joanna Tomasi, my former PhD student, which is now in a super professor, and also has a position in Ellery in Orsay. And she professes a lot of Brigitte Plateau, HDR, and PhD, were using the same approach to synchronization of events and Markov chains. And most of all, now we have a chance to have in our institute Aaron, who came to us. He's not only a member of Polish Academy of Sciences, but he's also a member of our institute, and he coordinates 2 European projects. We have a chance to work with him. And also, they take care about our research, specialized in intelligent energy error networks and the model. So I shall stop here. These are just few facts I wanted to underline as an introduction to our today meeting. Thank you.
At this point, the formal aspects are over, and we're moving forward towards the papers, the paper presentations. On a terminé la partie formelle des présentations, c'est l'introduction. On va passer maintenant à la présentation de la première communication. I was just wondering if there were questions or comments, because Tadek gave a very interesting historical perspective, and I was wondering whether any of you would like to ask questions about this or say something about this. No questions? Okay. I have a question for Tadek. And of course, we had, at the beginning, we had Professor Vegzi who came to Paris. He was already closely related to France, Lille and Toulouse. And he had this idea that this field that we were developing was of interest to your institute or to Poland in general. And then he convinced you to, and then a number of people came and visited and so on, and there was productive work with everything. Yes. What was at the institute side in Poland? Was there some industrial need that was driving this? Was there some other kind of driving motivation about this field and this work?
Most of all academic interest, but also Stefan Węgiel was supervising in the epoch some so-called national programs of introduction of small computers, mini computers, to control industrial processes. And, steel factories and factories of glass, factories of cement, and so on. And from his point of view, the essential question was the speed of the performance of the systems. So he had the idea that queuing theory may predict the speed, especially if we put priorities to. So customers represented programs, control programs, and there was a hierarchy of the execution. And how to attribute these priorities to have a desired response time of the whole system, which is a real-time system. So we started with models where sources of customers were just of number one. So each source was just one customer. And we attributed priorities and looking for the response time. And it was my colleague, Adam Polish, who is a professor at Berlin Technical University, and me who started to deliver some academic background for this project and program.
This is very interesting because it's perhaps one element that was missing from the perspective, which is the deeper motivation coming from application areas and so on. Alors je traduis pour les étudiants qui sont là, les étudiants français qui sont là, vous n'avez peut-être pas complètement suivi la discussion en anglais. La question que j'ai posée à mon collègue, à Tadek, c'était est-ce que donc dans cette collaboration, est-ce qu'il y avait une motivation peut-être industrielle ou vis-à-vis du point de vue applicatif pour les méthodes que nous étions en train de développer à l'époque à Paris, donc dans mon équipe, et pourquoi est-ce que donc l'équipe polonaise trouvait ça intéressant. Alors il m'a expliqué, il vient de m'expliquer, de nous expliquer qu'en fait, une des motivations, c'était que le directeur du laboratoire de l'époque, qui n'était pas le professeur Tchaikovsky, mais le professeur Tchaikovsky lui a succédé, donc le directeur du labo de l'époque avait un intérêt dans des grands systèmes de contrôle industriel, de commandes industrielles. Et donc, on utilisait évidemment des ordinateurs pour activer les commandes, et cela nécessitait une analyse de performance pour voir si les programmes qui faisaient la commande pouvaient s'exécuter à temps, avec des ressources évidemment limitées, puisque les ordinateurs s'occupaient de plusieurs commandes à la fois, c'est-à-dire de flots de commandes. Donc c'est dans ce sens-là qu'il y avait un intérêt. And this brings us, of course, to the Internet of Things, right? So it's exactly the same problems as we deal with the Internet of Things. And some of us very soon will be wired. I mean, we will have electronic pacemakers, electronic defibrillators, we will be robotic, we'll have robotic legs, and so on. There was a very interesting experiment announced just a few days ago in Paris about someone who was using his brain to drive his arms and legs, but through an exoskeleton, an external robot. So we will have these things, and exactly the same problems will arise in more complex and perhaps even more vital circumstances. Thank you, David. So with that, I would like to invite the first speaker. Oops. Okay. Okay, that's fine. As we were preparing the program, of course, the program committee was involved in choosing the speakers, and I'm very happy to have Professor Grozek from the Jagiellonian University in Krakow. He was nominated, he was invited at the request, a specific request of Professor Bernot, and we're delighted that you can join us. You may need the microphone.
Thank you very much for the invitation. I I'm indebted particularly because I'm a pure mathematician. So this is something extraordinary for me to be in such a group. I made my PhD in topological dynamics, so probably very far from your interest, but later I became interested in computational aspects of this theory, topological dynamics. The reason was, and I go a little bit in detail in a moment, the tools we were at hand for solving problems in differential equations were, differential equations were a great tool behind this technical revolution in the 17th, 18th century. But unfortunately, mathematicians could not contribute too much beyond this concept itself, because in terms of solving the equations, you have to rely on numerical methods. But surprisingly, it turned out that the topological methods may sometimes provide tools for proving the existence of certain solutions of particular features, but analytically it was very difficult to check the conditions. And we came up with a computational rigorous method. So we could somehow prove with the help of computer that certain solution exists. And this brings me now to the probably reason I'm here now. It turned out that this method also may be of interest when you study what I call data-driven dynamics. So nowadays we are in the situation where it's so easy to collect data, to store it. The computers are so fast, the storage is so huge. But the problem is how to get some understanding from this data. And topological methods, and there is a huge group of applied mathematicians worldwide now who use topological methods in understanding the geometry of data. This is particularly useful when the data is high dimensional, and this is typically the case. But there is less done in terms of combining with this with dynamic behavior. So here are just a few examples of data in dynamic nature. The top row, these are just examples of data collected from what is called time series, just records of certain measurements. The bottom row are just a few examples of a situation where you have a cloud of points, and at these points you can physically measure the direction of the expected movement in the nearest future. So this is just the case of sea currents. This is magnetic fields of the sun, and this is actually a study of brain. But anyway, so the question was, would it be possible to use these methods to understand dynamics given by data? And the question was, was it possible to adapt these topological tools? So this is the question. And one approach tested by many applied mathematicians was just to go back to these differential equations. So use this data to construct differential equations which are somehow approximates the problem, then solve the differential equation, solve numerically, and just use the solutions to understand, to predict the future. But this has several drawbacks. Let me mention only one, that you start with something which is discrete, and then you write an very artificial differential equation, and you have to discretize again in a different way just to solve it. So the idea is maybe it's more natural just to try to come up with a concept of dynamics in a purely combinatorial fashion and carry over these topological tools directly to this combinatorial setting. So what combinatorial tools do I speak about? This all has roots in the work of the Krakow mathematician Wajewski. I do not look this is a slide for mathematicians. Just this picture is important. This picture is important here. So the idea of Wajewski was just to understand he searched for stable solutions. or at least bounded solutions of differential equations, and he noticed that sometimes the study what happens at the boundary of the region may tell you what happens inside. And his observation was that if there is no solution inside, in this case there is one, there is a stationary part here. But if you just remove all the solutions which stay inside, then there is a continuous map from the initial stage to the boundary, which lets you make a topological observation that the whole region may be continuously deformed to the exit set marked here in red. So this is not the case. It's, even if you do not know topology, it's easy to imagine that if you want to transform this square into these two pieces, you have to break it. This will not be continuous. So this lack of continuity actually forces that something must exist inside. Okay, and then again, American mathematician Conley developed the Wajewski ideas into something analytically computable. He came up with the concept of isolating neighborhood. This is based on an assumption here. Vital for this continuity is the closedness of this exit set. And from that he developed, maybe let me go here, so this is Conley, he developed an index, a topological invariant, which when it's non-trivial, it guarantees the existence of bounded solutions, and moreover, if you know the invariant, you can predict the behavior of the solution. Is it attracting or repelling or is it periodic? And usually it turns form of a polynomial. So here are examples. This is the situation, this is just a pure situation of Wajewski theorem. If there is nothing inside, you can just follow the trajectories and deform the whole region to the exit set. And this is, the invariant is zero, the polynomial is zero. But, for instance, if you have a saddle, like here, then the invariant is just t. This is just, now you need to know a little bit of topology. The topological invariant of circle is the first homology group, which is non-trivial. This is reflected in this polynomial t here in the first power. So here is the summary of various cases. The point is that these different dynamical situations can have a description in terms just of the polynomial. And from this polynomial, you can just tell, for instance, that you have a rotating behavior, or which might be attracting. The polynomial is different. You have a rotating behavior which is repelling. The polynomial is different, and so on. The fixed points typically are monomials. Okay, so this theory, this Conley theory, found many applications in the study of differential equations, even to prove the existence of chaotic dynamics. But the question, now let me go, okay, the last thing about the theory, the Morse decomposition, the global description of dynamics. So when you have, when you want to have a global understanding, you can study several isolated invariant sets, connections between them, and build a graph, called the Morse-Conley graph, where you have these polynomials as labels in this graph, and this is a kind of global description of the dynamics. And the question now is, can we do something similar, but just directly on data? And here the work of Bioinformatics is very useful, and an American mathematician who at the end of the 20th century studied the question as a pure mathematician. He was not interested in data at all. Very surprising question. He asked himself, can I do Morse theory, the strongest mathematical tool in the study of connections between topology and dynamics, in purely combinatorial setting? And it turned out it's possible. It's very beautiful, this theory. I will not tell this theory here. The only point is that he came up as a byproduct with the concept of combinatorial vector field. So it's a kind of replacement of differential equations in purely combinatorial setting. So his space becomes now a integer complex, a collection of triangles, edges, vertices in this simplest case, planar case. This is emphasized here that actually this is a finite collection. I put a white circle in the center of mass of each piece. So for this triangle, this is this circle. For this edge, this is this circle, and so on. And then when you partition this collection of syntheses into singletons, which correspond in Morse theory to critical cells, and dubletons between face of codimension 1 and a triangle like this, you get what we call combinatorial vector field. And it turns out that, okay, so time. So there is a modification of this concept needed just because he was only interested in his concept to prove the analog of Morse theory, but this is not working well with general dynamics because sometimes when you have to pair, it may happen that you have to pair, for instance, three edges with the same two-dimensional cell. So there is this generalization, which I call combinatorial multivector field, where you are allowed not only to have a partition into singletons, so here is a singleton and dubletons, but sometimes larger corrections, as long as this is convex in the poset, defined poset structure defined by this phase relation. But anyway, the main point is that this whole Conley theory may be carried over to this combinatorial setting. So you still have all these invariants, all these polynomials. For instance, this is an example now. Again, Conley Morse graph. So there is, for instance, a repelling periodic trajectory here, an attracting periodic trajectory here, a saddle here, an attracting fixed point here, and so on. So you can compute these invariants. And interestingly, you can actually prove, this is what I managed to prove recently with my collaborators, that each such combinatorial vector field actually gives rise to a classical dynamical system. So this is not a pure abstract nonsense, this is always related to actual dynamics. Okay, and it works. This is just an example, a simple example, when we tested this on the dynamics we understand well. So we took just classical Lotka-Bortella equations, where the dynamics of the differential equations is well understood. And we were able to find that Morse decompositions, Morse sets. Okay, so the point is, here is the actual differential equations, but instead we just randomly selected a collection of points in the plane, assigned to the point a vector just from the differential equations. Here we have this, for control, this differential equation, and then, constructed the multivector field, computed the Morse decomposition, and there is this recent method of persistent topology, which lets you even look what happens when you gradually modify your grid. For instance, you take more and more points, and then the outcome of the computations may differ, but still you can recover these polynomials from these bars. But anyway, let me go now to this main example. So a few years ago, I had the chance to meet Gilles Bernal, who taught me the area of his research, where he studies dynamics of genes. And what I learned from this is that in principle, in theory, there are differential equations to describe this dynamics. But unlike the differential equations written by physicists, there is very little known about the coefficients in these dynamics. And moreover, the physicists can set up experiments to measure quite precisely the unknown coefficients. Biologists cannot. So they roughly know what the right-hand sides are, and they know that in principle there are these sigmoids curves. One of the approaches to study the problem, because of the complexity, in principle you could try to solve many differential equations for many coefficients, but it's probably too many to just get the idea what's going on. Instead, to concentrate, since the nonlinearities are the sigmoid curves, what mostly matters is where you have a small value or large value. And then you can just divide the variables into segments, where over a segment you can say here over segment 0 the control of these variables over the speed of the other variables is the same. It's low. Here one is low, one is high. Here both are high. So this way you divide the space into small pieces. By the way, these slides are taken from the presentation Gilles Perrineau gave at a conference in Poland in 2016. And then when you have such a division into pieces of these variables, you can just look from the possible states. So once again, low, 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 high, high, high. You can just draw these arrows which tell you roughly how the trajectories should move from piece to piece. So these are just two examples, but even in this combinatorial setting there are many, many possible dynamical systems. And I just thought that the methods we developed for this data-driven dynamics might also apply here. We have to dualize the space. So in these pictures, what matters are these squares, and the edges represents what happens between squares. To fit it to our language, we represent each square by a vertex, so we take a dual representation. Each edge here, horizontal, this vertical one is represented here by a horizontal edge, and for instance, we have this horizontal edge is represented here by the vertical edge, and so on. And now, let's take this example. This is Gilles' example, and this is reformulated in the language of these combinatorial multivector fields. And you can look for this Morse decomposition here, and the Morse Conley graph, and this is the Morse Conley graph here for this example. So for instance, what we see here, this arrow means that in principle you can expect that something will stay inside in this square. The same here. So we have two fixed points. This is represented here, and these are attractive fixed points. But you see that the dynamics from this square goes to this square, whereas something stays here. So when you understand dynamics, you know that there must be something which separates these two phenomena, and this takes the form of this fixed point here, which is actually a saddle, and its position in this Morse Conley graph is here. This saddle with the Conley polynomial t, which just tells you that this is a saddle, and the Conley polynomials here are just one, which tells you that these are attracting fixed points. So this is the other example. Here again we see this rotating behavior among these squares, which means that actually something must be fixed also here. So we have this repelling fixed point, attracting periodic trajectory, and again for similar results as before, a fixed point here, we see it here, but also this saddle here along this edge. So this is the Morse Conley polynomial here. You can notice that this one is not a monomial, and this is just because it corresponds to this periodic trajectory here. Okay, so there are these approaches now which people do for differential equations, but also somehow combinatorized, where in situations when you cannot tell precisely what the coefficients are, instead they try to do a full database. So just look over a space of parameters, divide this space of parameters into small pieces, and then try to classify all possible dynamical behavior over the whole space of parameters. So actually I asked my student to do something similar for this small space, but still quite interesting. And he computed all the possible combinatorial dynamical system on this space. So it's easy to count that the space consists of 15 cells, 2 squares, 7 edges, 6 vertices. it's also obvious to compute that there are 38,450 different combinatorial multivector fields on this space and 266 different Morse-Conley graphs. Different meaning they also differ by labels. So not only by the shape of the graph, but also what is at the labels. And this is now the collection of all these 266 Morse-Conley graphs. Of course, for each, this is not in this figure, for each Morse-Conley graph, there is the corresponding collection of combinatorial dynamical systems. They are ordered by the statistics. So this one is most frequent. So this Morse-Conley graphs appears in 5,000 something dynamical systems. So this is like the example we had here. So there are 500 examples of this, and so on. So this is his work. And of course, now the question is how to proceed, because this could be a starting point for a database. So somebody knows from the biological experiments that we expect a bistable, for instance, a bistable dynamics, and maybe one is like a fixed point, another one is oscillatory. So then you can search this database and produce all the combinatorial multivector fields which might be responsible for such dynamics. Of course, there is cost in such computations, an exponential cost. So if you want to take a larger space and do the classification, it's probably still possible for maybe 4 or 6 squares. This was done on a just average laptop, this computation just in a few minutes. Yes, I'm just done. So the last very comment is that even if there is a problem with this exponential growth, you can still combine the methods Gilles uses. Just to, when you produce the candidates, you just do the restriction. You do not look for all possible candidates, but just candidates which logically are acceptable and still produce a kind of database. So thanks a lot for your attention here.
Are there questions? Yes.
I have a couple of questions. One is from the physics side. If you formulate something in the form of differential equations, very often it represents a conservation loss of some form. Could you recast it in your topological language and from some invariants recover or have analog of the conservation loss and relate it to, let's say, to symmetries?
So the quick answer is we haven't tried that yet, but I see a potential for that too. But so far, nothing was done, at least from my knowledge, in that direction yet. But at least, surprisingly, so many important features really carry over to this combinatorial dynamics that for the moment I'm optimistic. When I started on this, it was a big barrier in understanding this spatial flavor of topology here, which was an obstacle which caused that we did not believe that many is possible. But then there was a switch, and suddenly it turned out that what is really important so far we managed to carry over. So this is all what I can say.
I think there's another question. There's a question.
There is also there, but
Let's start with that.
If you can what are the assumptions on the set on which you define this type of dynamics? So I understand it's discrete, but
yes. So in principle,
calculation points.
You can start with any cloud of points, then use the methods of computational topology to construct a simplicial complex. So for instance, Rips complex or Čech complex, and then you can build dynamics from this complex. That's the most typical situation. But as you've seen, the example with Gilles is completely different. It just comes from the division into squares of the spells via the places where you have a switch in the values, so that you cannot say that it's more or less the same parameter values in this region. So there are various ways to do that. But the typical one is just symmetry complex constructed from counterpoints via check complex or ring subclass, something like that.
We will take one more question and then we'll have to move forward. What was the other one?
So I thought you had also a question.
Well, I have a question too. So I'll be the last one. So,
can you ask the microphone? Please.
With respect to the methods you've presented, I would expect that the kind of the primary application area would be automata theory. Because there's such a direct connection. And I was just wondering, has there been an attempt to connect automata theory and structural transition matrices and automata theory and so on to the work that you are describing?
That would be definitely very, very interesting, but no attempt yet in that direction. I'm aware of this connection.
And just as a historical comment, this reminds me of the topological relationship, and automata theory. It reminds me of work in Grenoble with Yves Robert. There's a whole school of automata theory in France which developed in Grenoble, which was looking at the dynamics, essentially the dynamics seeking limit cycles and things of that nature for automata. And I think there's a strong connection with
what I can say is that I know they use in these areas this topology which are not convenient for typical topologies, namely where there is no metric space, no good separation axioms. And this is what happens here, and this is a barrier actually. So that is also a good sign that there might be something there too.
Okay, well, thank you very much. Thank you. Now we move on to a second presentation, which is not, may sound different, but not too far away. Laure Petrucci, who has worked a lot. Laure has worked a lot with Poland. She has published quite a few papers with them. And in addition, in fact, this paper, for instance. And in addition, I'd like to mention that Laure was proposed to speak here by Ferhan Pekerkin. He suggested Laure. They're from the same university. Thank you.
Thanks for inviting me. And so this work I'm going to present is issued from a collaboration with a group of Wojtek Pęczek and EP Pan in Warsaw. We had several projects, and there's an ongoing CNRS PAN project that Theophil will talk about tomorrow. So this is an earlier work. So this work is about controlling actions and time in parametric timed automata, and it was carried with Wojtek Pęczek, Michal Knapik, and Etienne André. Etienne was in the same group as I am at University Paris 13, and he just moved to Université de Lorraine in Nancy. So, does that work? Mm. Oh, sorry, it was switched off. Okay, so I will present some motivation, then show you what action controllable parametric timed automata are, and how we can do mixed parameter synthesis, and then some applications. So the motivation is to provide a designer with some design choices to support decision making in the system design process, where we have time characteristics that might be different. So when you design an electronic system, for example, you could choose between different hardware and that have different time characteristics, and you would like to have something to help you in choosing which hardware you're going to pick for your system. Another thing is that we are interested in enabling and disabling some controllable actions and seeing what is really meaningful there. So select choices depending on, for example, component costs and also feasibility. So there's a trade-off between constraints and also the actions that we are going to consider. So let's take a simple example. So I will show you a model here with a small automaton it's not the actual model that you'll see at the end, but it's just to give you a flavor of what's going on there. So this is a small example of a thief that wants to steal a treasure in a museum. So initially he is outside the museum and he waits outside. Then he can break the glass, break a window, and it takes some time, so at least p time units, and the alarm goes on. So when the window is broken, it starts beeping. Then the thief gets inside, he walks the corridor, takes some time as well, so let's say 2 time units, and he can steal this treasure. Then afterwards he wants here's another solution. The other solution is, instead of breaking the glass, it's to crawl in the ventilation system, and it takes at least q time units to get to the treasure room. And then when it steals the treasure, the alarm starts ringing, right? So it is, as you can see, there are 2 possible solutions. And the concern of the thief there is to say, well, which one am I going to choose? So finally, he wants to run away from the police because the alarm is ringing, and he has a possibility, which is to fly away. He has a buddy who is coming to pick him up with an helicopter, and to fly away takes him 3 time units at least. Or he can choose to go back in ventilation system and crawl again, and it takes the same time as on the way in. Okay, and let's say that it's safe if the alarm has been ringing for less than 15 time units, otherwise the police will show up. So here you see that we have both timing aspects. We have also the possibility of doing some actions, or choosing some actions, or not choosing the action, or choosing another one. Okay, so the problems are, the problems at stake here are timing problems on the one hand. So under which parameter values P and Q, we say breaking the glass takes at least P time units, crawling the vent takes at least Q time units. So under which parameter values PQ is this safe location reachable? And this is real parameters that we are considering, real timing parameters. And another possibility is under which parameter values P and Q is the location safe reachable if some of the actions that are at stake, so break glass, crawl vent, and fly away, are disabled, right? For example, it's too costly to have the helicopter picking you up, so you would like to avoid fly away. And this is some more parameters, so not timing parameters, but action parameters that are Booleans. Either they are enabled or they are disabled. So basically the goal is to build mapping from all the, from subsets of controllable actions to real parameter valuations, that is timing valuations, such that if these actions are enabled, then our goal, so safe here, is reachable under these valuations. So for if these actions are enabled, then we want to know the parameter, the timing parameter valuations that allow for reaching the goal. And of course we want to avoid brute force because we can enumerate everything and it takes ages, and this is not good, if possible. Okay, so we are considering action controllable parametric timed automata. So basically it's timed automata. Does this work? Yeah. So in timed automata you have locations. So here you have a source and a target. You have the real valued clocked. So here you have X and Y that are clocks there. They can be used in guards, so linear guards on transitions. So here it says that this transition from source to target, labeled by ACT, is enabled if the clock y minus the clock x is greater than 3. But they can also be used in invariance on state. So here you have something saying that in this state target, in this location target, the clock y must be less than 3. And there can be resets on transitions. So for example here, you can self-loop on this source state and reset the clock x. The transitions are of two types. So there can be time steps where all clocks are uniformly incremented. So the time passes at the same rate for all clocks. So x and y in this example will evolve the same way. There's no location change, so it's just the time passing in that case. Or there can be action transitions, and that is possible. So for example, this act is an action transition. If the guard is correct, is satisfied, and then the clocks that are reset, are to be reset, are reset, and we move to the target. So act moves from source to target here. And of course, the invariance on locations must not be violated at any time. So you can imagine, for example, if you're in this location target and you can stay on the y is smaller than 3. So if you want to let time pass, you can't let time pass more than 3. Okay, so a run there would be the following. Initially, we are in the source state, so that is the initial state. It's indicated by this small arrow. And initially, our two clocks, x and y, have value 0. We can wait, if we want, 3 time units. So if we do so, we stay in the source state, and both clocks are incremented by 3. Then a possibility is to fight the loop and reset x, so this one. And then in this case, we are still in the source state, because we loop on the source state, and clock x is reset to 0 here. But clock y is still 3. We can identify this transition act here, because we are in the source state, y minus x, so 3 minus 0 is greater than or equal to 3, so the guard is satisfied. The invariant at the end of the target state, y smaller than or equal to 3, is satisfied as well. And so we get to target state with 0 and 3 values. Okay. So here we are, so that was for timed automata, and here we are concerned with action controllable, action parametric timed automata. And we have, in addition to what I've shown you, we have parameters. So for example here, there's P, which was 3 in the previous slide. So we don't know what P is at the beginning. That is a parameter of the system. And so these parameters that can be used, these timing parameters that can be used in the linear guards on transitions and in the invariance of locations. The action labels, such as act here, they can be treated as propositional variables. So the action and parameter evaluations then becomes something from the set of actions and the set of parameters to the evaluation, which is Boolean for actions and real for the timing parameters. Okay. So here, if we look at evaluation V in this example, what happens? We would look in this valuation for all transitions that are not enabled, so for which the valuation is false. That means that these actions can't be taken, they are controlled as not being possible, and then we can remove them, and we can substitute all parameters P with the valuation, the real valuation of P. So if we, as an example, take this and say the valuation of act is true here, and the valuation of P is 3, well, what happens then is that we are in the previous case that I detailed earlier, and the target is reachable. That was the run that I described completely. If we have still the action act and the valuation of P is 4, what happens is that target is not reachable anymore because we can't have y minus x greater than 4 and y smaller than 3 at the same time. And if the valuation of act is false, that means that you can't take this transition and that the target is necessarily unreachable because there's no arrow getting there. Okay. So what we want to do is to know the reachability, a parametric reachability in such a system. And so we want to understand, to find all valuations under which a goal is reachable from the initial state. There was a theorem many years ago by Aller and his colleagues that said that this problem is already undecidable for timed systems. So, well, that is bad news, but the good news is that even for parametric timed automata, so without controlling actions, you can sometimes build the result by semi-algorithms, and these results are obtained. These algorithms are such that if they finish computing the result, then the result is exact. But it might be the case that they never terminate. So they would compute things. Eventually they will give you partial results along the way. And you know that in these cases, the reachability is ensured, but you're not guaranteed to have all possible parameter valuations that give you the result. But in practice, it works quite well. We have some tools. One of them is Imitator that can unfold the zone graph to synthesize constraints on real parameters using linear operations, and which is based on polyhedral calculus. And it's dedicated to parametric timed automata. And we could say, okay, let's use it and have a brute force approach and use to synthesize action and parameter values. We will iterate over all possible subsets of actions. Well, as you can imagine, that is very, very costly and not feasible in practice. And so we want to avoid brute force. At the same time, we have another tool that is called Spatula that was developed by the Polish team before this work. And it can synthesize sets of actions for fixed point properties of crypto structures using BDDs. So it's a very efficient tool. And our idea was to mix these two approaches to have Imitator preparing the zone graph with the timing constraints and Spatula synthesizing minimal sets of actions for the reachability in the zone graph. So that's the idea. So basically what Imitator does is that it will find zones, so tuples where you have a location, so the state in the automata, and a convex constraint over the set of clocks and the set of parameters. And it will build the zone graph by using several operations which are time elapsing, resetting of clocks, and projection of parameters. I won't go into mathematical details, but just give you an idea here. So let's take again this example. We start in the source state and with a constraint C, and when we fire the action here, when we take this action, then we start saying, okay, we'll get to the target here, and we had our constraint C, the zone that was on parameters and clocks. It has to satisfy the guard, so it will be intersected with the guard of the action. Then we will reset the clocks, then time can pass, and it must satisfy the invariant of the target. So basically that are the operations at stake when building the zone graph. So these operations may be quite costly. In spatula, with action synthesis, we start from a graph with zones as vertices and transitions labeled by actions, and then what we'll do is that we will look for the actions, the reachable sets that are sets of zones that are with these actions. Okay, so this is encoded using Boolean expressions on the actions. And if we take again our thief example, and we have break glass, walk corridor, fly away, and crawl vent as possible actions, then we can have a possibility that is sets of actions that include walk in the corridor and crawl in the ventilation, but not fly away. That is kind of the possible encodings that we can be using. So then the reachability is basically intersecting the zone with the actions reachable in the graph. That goes to the goals. So this is done using BDE-based fixed point synthesis for the existence of the goal, and it's expressed in parametric action restricted CTL, so one kind of logics on actions that is implemented in spatula. So to finish on the thief and treasure example, so you see it's a bit more explicit than the one that was at the beginning. So here we have this clock Y that must be greater than P to break the glass, and then it's reset to 0, so it's like a chronometer that counts the time that is passing in each action of the thief. And then when the thief is inside, it walks the corridor, it counts at least 2 units of time, and then it's reset to 0, etc. And we have this X here that must be less than 15, which is counting the time since when the alarm started, right? So we have some actions that may be enabled or disabled, so breaking the glass, crawling the ventilation, and flying away. And the parameters are the crawl time here and the glass breaking time here. When we construct the zone graph, we obtain something like this. And so you see there is in each state of this graph, we have a location and a constraint on the clocks and the parameters, right? And here, those that are highlighted are those for which we reach safe. Then using this, we can see what happens. So for the minimal set of actions that must be enabled with the corresponding parametric constraints, and so you can see different corresponding sets, and this is Okay, and so if you don't have flyaway, for example, and you want to crawl the vent and walk the corridor, then the time to crawl the vent must be less than 15. And that kind of constraints. So we can synthesize these constraints automatically. So this is not brute force, and if you look at the picture here, we have a comparison between this parameter synthesis and what happened on a brute force on a more complex example. Thank you.
A rather naive question from the side of graph theory. If you could explain, how could I understand this cast in the language of, let's say, simplest adjacency metrics, where you can have self-loops for taken at points and then wait at the links for time taken for various steps. How does this correspond to the spatula?
Okay. Actually, what we do is build a graph of all possible describing the behavior of the system that includes some parameter constraints, right? And then the techniques that we developed are basically exploring these graphs. So there are some things that might be issued from graph theory, strongly connected components and things like that. So, and search in the graph, search orders that might be important in the underlying techniques.
Other questions? And
Theophil's presentation tomorrow will talk a bit about this. How can we reduce this graph and explore them in a better way, so that
I have a question. I'm wondering, have you tried using this approach to simulate or to represent a system which is of realistic size? I'm thinking, for instance, it looks very similar to things people might do in emergency management.
Yeah.
When you're moving people through a building, through a large building, or perhaps even in traffic control.
Yeah, so the other example was the classical train system, train and gate controller system that has been modified so that it is both scalable to try different sizes of the system and also more complex than the usual.
How big? How many trains? How many rail lines? How many?
Let me think. We scaled on the trains. Can't remember how many, up to how many we got. But we scaled on the trains. We added some intruder that could enable or disable some sensors. So that was the kind of scalability things that we did. Yeah.
Okay. Right, thank you. Thank you very much. Thank you. Let's thank the speaker. And the next speaker is Nicolas Gast. He's arriving. And I think his talk has just been put on the machine, the computer.
Okay. Yep. So thank you for the invitation. And today, what I want to talk about is a model of say, population of stochastic population dynamics that is called mean field approximation. And in particular, I will try both to explain you what it is, but also explain you where it can be used and where it can be what we call like refined, in particular for small populations. So the general model that I will look at is that you have a dynamical system where you have a population of objects that we assume that does not move, there is no arrival of objects, and each object has its own state, that evolves in a discrete state space. And the dynamic of these objects are that, if I look at one particular object, say I, it's, it jumps from state I to state J with some probability that depends on the population, on the overall population dynamic here. And in particular, here I'm writing like xi would be the fraction of objects that are in a given state. So this is to represent maybe the average state of an object. And here, the state of one object is like a Markov chain if you condition on this capital X. So I jump from I to J with this function qij that depends on X. So I'll give an example more precise just after that. But say that this kind of models appears widely in like game theory when you look at like replicator dynamics, where an object tries to imitate the best behavior of people, or in biology where you have a cell that is interacting with another cell, for example. Or my example would be in computer systems when you look in particular at decentralized allocation strategies. So in this talk, I will talk about the general class of model, but I will more specifically use one example, that is the first model, that is a so-called load balancing example, where the idea is that imagine that you have a bunch of servers that are represented as queues here. And here, each of these black square is one customer in this queue. And okay, each server is independent and serves its own customer. But what we do here is that when a client or a job arrives in the system, what we do is that we sample a number of servers at random, and we allocate this job to the least loaded of these servers. So for example, here I sample 2 queues, and I would allocate the job to this queue that is empty, rather than to this one that has 3 jobs. Okay, so this model is like a rather simple population model, but it has some kind of a complicated dynamics. And just as another example that we'll see if I have time to describe it at the end, this second model is also of the same spirit. Is an example of infection propagation, where here you could imagine this is like some SIS or SIR example, where each agent has different states. Either like it is infected, or here I call it active, or it might be susceptible or dormant. And then, depending on who he meets, who he encounters during the day, he might jump from state, for example, dormant to active, or from state active to susceptible again. Okay, and this kind of like infection model are also quite popular in this epidemiology literature. So when you look at such a model, maybe I'll jump directly to this thing. It's rather common to use 2 kinds of models to describe the dynamics. Either you use a stochastic model, or you use more dynamical system approach, and you write directly the ODEs that corresponds to this system. And the mean field approximation essentially is the solution of this system of ODE that you can write. And here, what I want to talk about in this, in this session is now, if we go back to the stochastic system, what does the ODE tells us about our stochastic system? And in particular, what is known is that mean field approximation is exact when the number of objects goes to infinity. But what I want to study a bit more is what happens when the the number of objects is not infinite, but it's moderate or even relatively small. Okay, and so this talk is really about like how can we use a dynamical system approach to study simple stochastic systems. Not simple, but small stochastic systems. So here's the outline. I first want to give you some basics about mean field approximation, and then we see how we can like refine it to small population sizes. So okay, so to go back on my example, here I'm assuming that I have n servers. Jobs arrive are allocated to the shortest queue among d queues chosen at random. And I'm assuming that the time it takes to serve one server is exponentially distributed of mean 1 to simplify notation. So essentially in this model there are two parameters. One is rho, which is the load, which is the arrival at a given server, and the other one is n, which is a number of servers that I have in my system. Yeah, and another one is d, but okay, d will be considered fixed. So the natural representation of the state of the system would be to look at what I call Sn, which is the state of every object in the queue. So here, for this particular model, the first server has 1 job, the second 3, 1, 0, and 2. So the natural representation of the state space would be to consider this tuple of variables. Now, of course, because I said that all servers are identical, this is not the most compact representation of the system state. And also, when n is large, when the number of servers is large, this grows exponentially. I mean, the number of possible states grows large. So like a more interesting, powerful representation is to look at this state capital X, where here xi would be the fraction of queues of servers that have I or more jobs in my queue. So of course, x0 is 1 because they all have at least 0 jobs. And here for this particular state, I have 5 servers, so x1 would be 0.8 because like 80% of these have 1 job or more, and 40% have 2 jobs or more. And none of them have 4 jobs or more. Okay. So now this is an infinite vector in theory, but if the queues are bounded, this will be finite. Now, when I look at this representation of the state, I can construct the transition of my states. And there are two kinds of transition. Either I have an arrival of job or I have a departure of a job. And here for this particular representation, if I have an arrival of jobs at a queue that has I-1 job, it will just increase the ith coordinate by 1/n, because my x is a fraction of servers that have I or more jobs. And a departure of a queue with I jobs will decrease this, this by 1/n. Now, I said that departure occurs at rate 1 for a server, so this is rather simple, but the question is more like when I want to compute at which rate arrive jobs, what is the probability that when an arrival occurs, it is allocated to a server that has exactly I-1 jobs. Said otherwise, like if you pick 2 servers at random, what is the probability that the least loaded of these 2 has exactly I-1 job? Easy question has an easy answer, but yes or no. It depends if you pick the 2 servers, say with replacement or without replacement. Like it depends if you want to pick 2 distinct servers or not. If you pick servers with replacement, so if you don't force yourself to pick them 2 distinct servers, then this probability is rather simple. It's just xi-1 squared, because this is a probability that when you pick a server, it has I minus 1 jobs or more, and minus xi squared. So this is the probability that the two servers have both more than I minus 1 and not both have more than I. Now if you pick them with replacement, it's a bit more complicated, but as you can imagine, when n is large, it doesn't make really a difference. I mean, when n goes to infinity, this thing converges to this one. And that's why in the literature, I mean, most people just focus on this problem. So to summarize the transition on my system, what I have is that my vector, infinite vector x, like grows increases its ith component by 1 over n at rate n rho times this polynomial, and it decreases at a rate n here that is linear because here all servers are independent. And what is called the mean field approximation of this system is just the ODE that corresponds to these average variations here. So in particular, this is an infinite system of ODE, but the derivative with respect to time of the ith coordinate would be just rho times this arrival here minus 1 times this thing here, okay? And more generally, you can imagine that variant model of this system, I won't describe all details, but for example, there are variants of this system where when a server has no job, he will pull jobs from other servers, and this can again be described as a variant of the model. Or you can imagine that you have some kind of super server that will go to the, for example, most loaded servers and will try to help them, and this can again be modeled with such a model. And in all these systems, you can write a similar system of ordinary differential equation that has more or less the same form as before. And in fact, this model is not just for like this load balancing mechanism, but it's an instance of models that are called like density-dependent population processes that have been introduced, let's say in the 70s, where here I'm looking at stochastic model where x is imagine like the population, the number of objects or the fraction of objects that are in different states. And here, the transition of this system are like x goes to x plus L over n at some rate n times beta L of x, where L would be the my changes like it says for example one people from this state goes to this state, and here this n is the size of the population, so the thing that scales. And what we're assuming is that as the population grows, each transition affects a smaller number of people, but the rate at which it occurs grows with the system size because more people are interacting. And for this system, like the mean field approximation is just the solution of this ODE, where the ODE is the average variation of the system, which essentially is the sum of all transition of the delta of this transition times the rate of this transition. Okay, so what is known for this system essentially is that as n goes to infinity, mean field approximation becomes accurate. Okay, this can be translated into convergence in probability. And also, similarly, like if the dynamical system has a unique attractor, not cycles or anything, but just a unique attractor, we can do the same convergence result for the stationary behavior. And just to look at one numerical example, here, what I draw in this table is that I pick different loads, different parameters of the system, and different system size. And on the right-hand side, I compute like the steady-state average Q length predicted by my mean field approximation. And here, I compute the steady-state average Q length using just a simulation of the stochastic system. And what you see is that when n is about 100, I mean, these numbers here are like a good prediction of what happens for the real system. So it's given efficient quantitative tool to study such systems. And the model itself is not important, but just say that if I took a variant of this model, I again have something that is also quite accurate for n equals 100. Okay, so more precisely, where does this 100 comes from? One partial answer that has been found is that if you look at population system, like the most simple approximation of a stochastic system is a deterministic system, and say a bit more accurate approximation is to look at a second order approximation, which is a diffusion approximation. And in particular, it can be shown that if you look at my stochastic process x, as n goes to infinity, it is indeed well described by some diffusion approximation. That is, here my small x would be my solution of my ODE, and the second term is a diffusion term. And that's what you sort of observe here on this curve. Like the curve in blue is the ODE, and then I plot three different sizes, like n equals 10, 100, and 1,000. And you see that, first of all, the red curve is roughly equal to the blue curve plus some Brownian motion around it. Okay. But here, I mean, if you look at the green curve, it is still pretty far away from the actual solution of the differential equation. So why was the approximation really working for n equals 100? So in fact, if you look at my average Q length, still on my same example, and you look at how does the average Q length evolve with n, and here, particularly, I chose like n equals 10, 100, and 1,000. And this is the mean field approximation. So of course, you observe that this converges to this value, but also that the error that is the error that is made when you subtract this value minus this value is roughly of the order like here it's roughly 4 divided by n. Okay. Which is not my 1 over square root n of just before. And in particular here, I mean the orange curve seems really, really far away from the blue curve. Okay, of course it's just a discrete curve. Whereas here, maybe it's not, it is not close, but it's not too far away. And in fact, this is like a general result that you can prove is that if you look at here, an average Q length, it's an expectation of the system. An expectation of the system is close to the mean field approximation, and the error decreases like 1 over n, okay, as the system size grows. And this is just like if h is a smooth function, expectation of h of xn is equal to h of x plus a term v over n. And the nice thing is that this v over n is a solution of a differential equation also that it is easily characterized and that it's easy to compute numerically. Now I won't explain you really in details how you compute this v term, but just to say that essentially it depends on the first and second derivative of my f function before. And if you know how to compute the first and second derivative of your drift, then you know how to compute this v. And the differential equation is not really pretty, but it's, again, easy to solve with any numerical library that knows how to integrate differential equations. Now, if I go back to my example, okay, sorry. Here I say that the expectation of xn is equal to x of x, my mean field approximation, plus this term vt over n, plus I should have read there are some smaller order terms after that. And this thing here, this x plus v over n, is what has been called this refined approximation, because you refine the term by some v over n. And now if you go back to my example and you look now, how does this refined approximation compare to the like true value that we estimate by simulation? Now in fact, so the first line here would be the value that I obtained by simulation, and the second line is my fixed point plus some term v over n, where v here is roughly equal to 4 here. So my second term is like this term plus 4 over n. And what you observe in this figure is that, in fact, it's really a good approximation of what happens in reality. And here, what you have to imagine is that to obtain this number for n equals 10, what we did is we look at the values, that is the limit as n goes to infinity. We look what is the rate of conversion to this value as n goes to infinity. And then you apply this correction term here and here, and it gives a good estimate of the. I mean, it gives good estimate, sorry, of this of the value here, of the true value. But also it gives the estimate that is much more accurate than the value that is provided by this classical mean field approximation. Similarly, if I look, this is just another example. Here for n equals 10, we are really far away from this value, but the refined approximation gives a really good quantitative estimate of the performance. Okay, so to conclude, what I describe here in this talk, I talk about this mean field approximation, that in fact mean field approximation can be viewed as an approximation where for stochastic population process, where you assume that all state of the agents are independent. And that's how you can construct also this approximation. So if you look at this approximation, essentially what we need is that if we have some smoothness condition of the differential equation, then we have an 1 over n accuracy of the method. Everything works well, and we can use it to define a refined approximation. And in most of the cases that we've studied, this works really well, even for population size that are pretty small. So essentially, it gives you really accurate numerical method to study quantitatively what happens for a stochastic population process. So we can do it for steady state analysis or also transient regime, which is also convenient. And we can do 1 over n term, but I mean the 1 over n squared term can also be computed, even if it's a bit more involved. Now, of course, I would say this does not always work. One of the first limits of this is that this works when you want to study properties that depend on the expected value of the population. Okay, so for example, if you look at a queuing system, the average queue length is an expected. It can be written as an expected value of the population. But on the other hand, if you look at, for example, what is the probability that my system has more than 100 jobs, this does not depend on the expectation of the queue length. This is really a probability of my population. So this is something that you cannot do. And the reason why is that because the population has a really stochastic behavior, and so you cannot, I mean, there is this 1 over square root n times this Brownian motion that you will find here, and you cannot go away. A second limit is more linked to dynamical system analysis. I mean, we've seen earlier that steady state analysis of dynamical system are really complex. Okay, and in particular, it's quite common if you pick a random dynamical system that has cycle limits plus maybe some points that are local attractor plus some, all kinds of different behavior. And in particular, this example here is just a two-dimensional dynamical system where there is a unique fixed point, but there is a cycle. And in fact, if you look at the trajectory of the dynamical system, they converge to the cycle because the trajectories go away from the fixed point. Okay, the fixed point is not an attractor. And if you look at this system, what is interesting is that just by modifying just a bit the parameter of the differential equation, the fixed point can be an attractor or can can repulse the trajectories. And now, if you look at what gives the mean field approximation of this system, then in fact you realize that the mean field approximation is not really working well because it predicts a cycle where simulation, whereas the stochastic system, its particular Markov chain always converges to its stationary measure. And if you look at refined expansion, it gives like all sort of crazy dynamics that essentially says that it's not just numerical instability, it's just really the method is unstable when you have this kind of limiting cycles. Okay, last thing that I would just want to mention, mean field approximation nowadays is also quite popular because of mean field games and games theory. And there is some connection between what I've said and mean field games, but it's not completely obvious that a game with n player always converges to a game, to a mean field game. In particular, it's not always odd. So thank you for your attention.
Questions? Yes, Gerardo. Go ahead. Oh, you need the mic.
Nice talk. Concerning the transient distributions, there is a famous paper by Shrikant analyzing a specific family of models, peer-to-peer systems, where he used the central limit theorem for the diffusion approximation. In your experience, adding the diffusion term, don't you get already a nice approximation of the transient, or doesn't always work for small t, for instance?
So I think it depends what you. It depends again what you want to track. Like here on the left, this is really like the stochastic trajectory are really close to the mean field approximation plus this diffusion approximation that you can put on. And so if you want to study the population dynamic, this capital X, then it really works well to have this diffusion approximation. Now, what this diffusion approximation, what it does not give you is, for example, when you want to study how does the expected, for example, Q length evolve with time. So you want to remove, essentially, if you want to remove this the noise that you have in your simulation. Now, if you take the expectation of this term here, it's quickly that the G is centered, so the G goes away. And so it's not precise enough to give you a better estimate than just this approximation. Okay. And that's where you need the second term, essentially, is a 1/n that comes here.
May I ask you, in your simulations, what kind of distributions are you assuming for the arrivals and for the services?
Okay, say that for now, the only thing that I know how to do is exponential distribution, so Poisson arrivals and exponential service time. Of course, if you have like phase type, it would be doable too, but like more general distribution than that.
Yeah. Well, okay, but that's why you're getting these good approximations. If you move away from those assumptions, then we're back perhaps at the question that Gerardo was asking, how to approximate when you don't have exponentials. See, that's a challenge, I think. That's what he was pointing to in a certain way.
Yeah.
I assumed that you were using exponentials. Mm-hmm. Kind of understood that.
Yeah.
Okay. Fine. Thank you very much. Okay, I'm the next one. I'm the next speaker, so that's easy. Let me just say a few words of introduction not of myself, but of the work, as I start my presentation. The work is, strangely enough, not my most recent work. So a lot of my recent papers, you can look, for instance, at the Journal of IEEE Systems Journal, they're about energy issues. Or I have other work, energy and ICT, energy and computing, and I have other work, also recent work on IC information, networks and computers, and security. So those are the areas in which I've been publishing recently. However, this work I'm talking about because it hasn't been picked up as much. For instance, if I were going to talk about energy packet networks, no point in doing that. Jean-Michel will talk about such things later. So I'd rather talk about something that has perhaps been less picked up. The only people who've picked up on this work over the years are, well, one of my students got a PhD, and because of the subject he worked on, he got a very nice job at Zurich Re. That's also an interesting application of a PhD, getting a nice job. And then people at Tsinghua University have expressed interest and have worked on this, on related problems. And people in Hungary, some information theorists in Hungary have worked on these models, okay? But other than that, it hasn't been picked up. So I'm kind of talking about it now, so perhaps someone else will pick it up and do something with it, okay? So it's about networked auctions, and the base paper is quite old. It's 10 years old. So it's ACM transactions on internet technology. And why that journal? Because the ACM transactions on internet technology published a lot of papers, and still does, on mechanisms and auctions. So on economic models applied to computing issues. So economic paradigms applied to computing issues. That's why I had published it there. And recently, there have been these transaction papers and some conference papers and so on taking this approach to represent auctions in telecommunications. As you know, in telecoms, there are different kinds of auctions. The most common one is where they auction actually bandwidth, when they sell bandwidth and they set up auctions, but we're not talking about that. The applications here are about the following question. Suppose that many telecom users have a contract with their internet service provider, with their mobile service provider, saying you have so much bandwidth, okay? And this bandwidth, say they have so much bandwidth per month. So they've paid to get, I don't know how many gigawatts. I didn't mean W-A-T-T, I meant giga W-H-A-T, some unit, okay? So they've paid to get so many gigabytes or whatever of bandwidth. And as the month goes by, so they have this at the beginning of the month, it's been renewed, and as the months go by, the month goes by, they either are very close to exhausting it, using all of it, or they have not used it, okay? So the applications here are about how you can use auctions so that those who have excess bandwidth can dynamically, automatically sell bandwidth to those who have not enough, okay? So that the ones who have excess can recoup some of their money, and the other ones would, of course, pay something to this individual who is giving them bandwidth, okay? So that's the application, and the whole issue is how to model, analytically, how to model auctions. Now, when I started this work, and when I started this work, my motivation wasn't that. My motivation was much simpler. Let's see which button I push. It was that the world is going towards a system of electronic transactions. Okay? So a lot of the things that we're doing, for instance, in finance and so on, we're doing automatic transactions. And therefore, it would be very interesting to be able to model economic transactions using analytical techniques. So let's go forward a little bit with the background. So at that time, when I got into this problem, at that time, I was working with people like Nick Jennings, who was at that time at Southampton, who is a kind of a big auctions and mechanisms person. And I was trying to understand what was actually happening, because if you look at the literature in this field, the literature is essentially simulation. So you have a very hard time understanding or reproducing, if you wish, the results they're claiming, or understanding how they have reached these results, because it's all based, I've done this, here's the mechanism, and here is the simulation result telling you that this is working or it's not working. So that was the the motivation. It was really to build some math underpinning the way these mechanisms were being represented. Okay? So we have to have a certain number of quantities that we define. We are talking, you can think, let's start with a single auction. I will then go on to n auctions operating together. But let's start with a single auction. Now, in a single auction, first of all, there's the value of the good. The value means how much it is worth to the buyer, okay? That value can be a random variable, okay? We assume it's a random variable. This value, of course, will evolve with time, but let us assume that it's a stationary, it's a time-independent random variable. The buyers, obviously, will not bid above the value. So if they know that this is worth 100 euros, they will not easily pay 101, 102, and so on. But you may have a certain bidding probability associated with the value of the good. The other aspect which is very interesting is that the seller, okay, in all auction systems, the seller has to, at some point, either decide that it has received a better bid, and therefore the previous bid is out of the picture, or it has to answer the buyer by a deadline, okay? So the model also has a deadline, which again can be taken to be a random variable. Then there's the issue of the price. So what is the price? The price is a random variable as well, but this is a dynamical system now, if you think about the price, because the price is evolving with time. How does it evolve? Every time there's a new bid that comes in, this bid is, of course, above or equal to the previous price, okay? So it's an increasing function. This random variable representing the price is an increasing function over the lifetime of a single auction, okay? And when the auction is over, what happens? When the auction is over, the price drops to zero because you're starting a new auction. You can make various changes on this basic model. For instance, you can consider that there's a reserve price. That is, you will never sell unless the bids exceed a certain value, okay? But that's kind of a detail in the context of a mathematical model. So I won't go through the whole history of these things, but try to show you what it looks like. So the simplest model you can imagine is a Markov chain, okay? The Markov chain has, it represents what? First of all, it represents the price going up, and when the sale occurs, the price drops to zero, okay? After the price drops to zero, you will have a dead time when the whole auction resets itself, and then this is repeated as a renewal process, all right? Then you have bids which are arriving, and you could assume that bids arrive according to a Poisson process. Why not? It's a good starting point. So bids arrive according to a Poisson process, and the bid arrival rate can be modulated by the value compared to the price. So if the value is way higher than the price, the arrival rate might be at that time a bit higher. The value below the price, then this would change, okay? So you can have that, and then if you analyze things, you get some very nice, get some very, very nice results in the model, very simple results, very clear results. For instance, the expected sale price given a value has the following form that you see there. I don't know if the pointer works. I suppose it does. No, it doesn't. Okay. So what you're seeing there is 1 minus rho to the power v over 1 minus rho, where rho is the ratio of the arrival rate to the arrival rate plus the delta is the acceptance rate. Okay, 1 over delta is the average time it takes the seller to accept the bid, right? Of course, any bid will be superseded by a higher bid. So you have this very simple representation, the sale price and the income per unit time, okay, that you can get. And this characterizes the behavior of the auction, of the single auction by itself. These are results coming out of a fairly simple Markov chain model. There they are summarized in this form, the expected income per unit time. Now, you have a detailed Vickrey auction. Now, the model I described with, a bid comes, if it's higher than the previous bid, then the previous bid is annulled, and the process continues, and the seller has a fixed timeout. If it doesn't receive a better bid, has to sell to the highest bidder. This model is known as an English auction. There are many variants, and there are variants called, for instance, the Vickrey auction, where the highest bidder gets the object that he's trying to buy at the second highest price, not at the highest price, the second highest, because you say, we will sell it to you at the price that someone else is bidding, okay? So in that case, you will have a different formula, but basically it's all kind of the same thing. So from here, auctions with a minimum sale price, I mentioned that, it can be S, this is called a reserve price in an auction. Then there are questions of, suppose a bidder is unsuccessful, what is the probability that it comes back? What is the effect of this on the model? Okay, and that's what's discussed there. And this is kind of the numerics, which is interesting. The D there is in fact delta. The D along the x-axis is delta. And the y-axis is the income per unit time. Why do I say income per unit time? Because if you're a seller, you are not really interested in the price that you get for one bid, because you're also optimizing time. You are interested in how much money you're making over time, not how much money you're making over individual auction, because you could wait indefinitely hoping to get a very, very high price, and you would perhaps get a very high price. But by that time, you would have wasted a lot of time. So you're interested in the throughput of the economics transaction. If you're running, for instance, a website selling, I don't know, washing machines or something, you're interested in the throughput of this website in terms of money per unit time, not in the highest money you've gotten for a dishwasher. So you're looking at that, and it's quite interesting that for the seller, there is a parameter of optimization, which is how long she should wait before accepting the bid. Okay? So if you are to the left-hand side, it means that your time is very long. Okay? Left-hand side, the time of waiting is very long, and what's happening is the price, the income per unit time is very low. You're waiting a lot, hoping for a high price, but you're not making any money. And at the right-hand side, when you go to the right-hand side, then you're deciding very quickly. And between the two, there is an optimum. Okay? So that's kind of interesting. More about various things, curves of this type. The effect of distributions regarding the value, V. Okay, the small v is the value. You can assume it has a certain distribution or another one. How robust are results to the different distributions. The difference between an English and a Vickrey auction, and so on. So you can keep on doing this. The effect of the probability that the buyer comes back and how that influences your income. If you have persistent buyers who are happy and they're coming back, obviously you're going to make more and more money. So all those things can be analyzed in this model. Okay? Let me move on now. There are quite interesting things about price formations. I won't talk about them, but basically, what you have are bidders who are observing the auction in which they're going to buy, okay? So by observing the auction, they have a sense of what the value is. So if they do some kind of optimization to understand this, then you will have fixed point equations describing what the buyer knows and its arrival rate and what the market is doing or the auction is doing in response to this. And that gives you some rather neat results, but we'll just skip all that because I actually want to go to networked auctions. Okay, I'm skipping a lot of things and going to network auctions. Now, what's a networked auction? And there's an interesting, what the main bottom line is that the networked auction will have a very nice product form result solution, okay? Which is different from Jackson networks, different from BCMP networks, different. It's a new product form solution. So what does the system look like? Well, now, each auction is represented by two integers. One integer is the price at that auction, okay? What is the current price at the auction, so that you have to bid above that price to be able to buy. The second integer is the number of buyers sitting at that auction, okay? So the auction is the price and the number of people sitting there, okay? And these people, the assumption is, if someone is sitting at can't be sitting at another auction. So you have a motion of buyers who go from one auction to the other in the market, okay? They have different places where they can buy something, so they will move around, perhaps as a function of price, a function of other things. So they're allowed to move around, and the motion is a Markov chain. So all of this model is Markovian, everything is Poisson, everything is exponential. So they're allowed to move around, and every one of these auctions has different parameters. For instance, different, okay? And the arrival rate of buyers to that particular market will be different. That particular auction will be different from the arrival rate, the net arrival rate of customers at the other auction. So you have this kind of very interesting model. It's a mobile bidder model. So you move around as a function of your interests. And you have external arrival rates for each of the auctions. Of course, you're going to have flow equations, which represent the total arrival rates, because some people will leave one auction to move to another one. Then you have the departure rate, which will depend on these two variables, y and x, that I mentioned. Now, the departure rate for an auction will depend on the number of people sitting there, except yourself, so you'll have a departure rate, and then you'll have some other quantity, which is a basic parameter of the system. So you're going to have individual departure rates. You're going to have different values of the goods, okay? So you have all of these things mixed up into this representation. So look at the departure rate, for instance. It depends on the number of customers, -1, why -1? Because the one who has just bid is stuck there until it is taken. That person is not going to leave, okay? Stuck there, so you have y -1. Then you have some local constant, beta, and then you have a term which depends on the price. So people will leave an auction if it's just too expensive. So you're going to have a rate of departure which will depend both on the number of people sitting there, on local parameters, and also on the price. So these are interesting ways of representing the system. Now this leads, of course, differential equations are not in mean field approximations. The differential equations are also the Chapman-Kolmogorov equations. So we have the differential equations representing these n auctions with two integers for each auction, the price and the number of people sitting there. You have state transitions, and you can enumerate the state transitions. And then you can build marginal equations for numbers of bidders. There is one basic assumption under which the model is being solved, And this is the so-called active bidders assumption. What's the active bidders assumption? It says that, if there is a single bidder sitting there, then if the number of bidders is at least one, okay, then the price is also at least one. It means that if a bidder arrives to an auction, okay, and finds no one, immediately, and the price is zero, immediately, okay, it will make a bid saying, this is kind of very cheap, I'm not there to look at a window, I'm there to buy. So if I see the price is really zero, then I will immediately bid, and so you have an immediate transition into the one state. So that's just the single assumption that limits, if you wish, the model, and with this, one has basically a product form. And the way you solve it is that you first solve the marginal equations related to the number. You look at the steady state related to the number, and then from there you go back into the joint probabilities and you solve the joint probability distribution. So that's really all I wanted to say. There's a lot more to be said about the subject, but it's kind of interesting, and I hope it raises some interest among some of the researchers, students sitting here. And I'm ready to answer questions. Let me go back to any questions? Yes? Well, the simplest case is that they have some arbitrary Markov chain representing the movement of bidders, okay? The departure, though, is state dependent, right? So you depart because the price is too high or whatever. So you have a state dependent departure depending on the price, okay? Now, you can also get a product form if you assume that the arrivals are state dependent, dependent on the price. So that's basically the model, which means that you still have, then in that case you will have state-dependent transition probabilities from one place to another, okay? And you'd have state-dependent, of course, departure probabilities from any state. Both are possible. So decide wants to continue and buy other things, free to do so, may go somewhere else, or may depart the system. Yes? Well, it depends. If I'm buying something, say if I'm buying a car and I'm looking at different auctions, I can't buy 5 cars at the same time. I have so much money and I buy one car. So I concentrate on one auction, put my attention there, and so on. So it really depends on what model you're looking at. The case where you try to buy many things at the same time, I can't think of many practical situations where that would happen. I can't really think of, but I'm sure that you can imagine situations. No, not at all, because bandwidth is one user selling bandwidth, okay? So many users selling bandwidth and many buying. But they buy one at a time. They're not going to say, I buy 3 from you, 5 from you, 7 from you, etc. They buy one at a time and they try to get what they need. When they need again, they will try again, or if they don't have enough, they will go again. So it's, the individual, the idea is that the individual decides on a purchase one at a time, not simultaneous purchases. It would be kind of even very difficult to do any optimization, even, you're going to have NP hard problems of optimization algorithms and so on. Yes?
So because maybe it's very possible. Just imagine that you have the bidding process, and the second last bidder bids in some reasonable price. Then comes unreasonable bidder, sort of difference, which practically cannot be outbid, immediately secures the price of the previous bidder. How can you sort of protect yourself? There's no possible interest of this business.
Well, you can, the formulas I gave you are for the case. I mean, this is a mathematical model, so everything is not included, but the formulas I've given you is where bidders are incremental. That is, if I have given a bid, and what do? I look at, if I'm going to give a bid, I look at the other guy, and I bid just above, hoping to get it. Okay, so it's a kind of a unit increment type thing in the analytical models. But you can have jumps. You have a random variable which represents the jump, which is, in that case, equivalent, essentially, to that model. Now, your case is where the random variable has, you know, a very large distance between, you have two values, you know, or a group of low values, and then the exceptional values once in a while. And one could analyze this.
I'm not an expert of auctions, but so there is often a game theoretic aspect in it that users at a given auction interact in a strategic way. So here they interact in a stochastic way, which is this, you look at how many people there are, and you look at the current price or whatever, and then there is a random process of the, but so could you incorporate this strategic aspect between, in your model?
Yeah. Well, we did actually, but that was in the case of a single auction. So in a single auction, we looked at many strategic cases like that. And this is what got my student the position at Zurich Re. Quickly after his PhD, got a very high-paying job, way above my salary. But so we did look, but for a single auction, when you're in the network case, which in a way is more interesting, it becomes very difficult to do any analysis and to get any results, at least for me. Other questions? Yes, sir.
Quite often in the situations like bandwidth, the value is connected with the timing. So I need bandwidth from, say, tomorrow to day after tomorrow, or tickets for the theater performance. Right. So therefore, the value of the bidding part is declining when the deadline comes, because of course you cannot buy the ticket when the performance started or is going on. And the same story in bandwidth. Did you take that into account? That
Well,
this
yes,
is
because the transaction doesn't happen unless it's available immediately, right? So this is exactly the assumption, so that you bid, and at that time you get it if it's there. If it's not there, you're not getting it. So that's the assumption that we made in the two papers that I mentioned about network bandwidths.
But from the seller point of view, it also underlines this element mentioned. The seller has to take into account waiting too long.
Right. That over the month, you know, as he gets very close to the end of the month, the fact that he has extra bandwidth is worthless.
Right.
Yeah. Anything else? Other questions? Well, thank you very much. It arrives at the right time. I was actually watching the buffet over there to time myself. As the doors opened, I said, I have to finish.